Welcome back, everyone. This is Dr. Gallenstein. We're doing the last lecture on demand. Today, we are going to do something a little bit more technical and mathematical. I'm going to introduce what's called the Slutsky equation. The Slutsky equation, and what this equation is going to do is it's going to relate. It's going to mathematically decompose the impact of a price change on demand. All right, so we're kind of continuing our discussion of price changes. So if I want to ask the question, what is the effect of an increase in the price of coffee on demand for coffee, I want to know the answer to this derivative. Well, today I'm going to walk you through the steps of knowing what the answer to that question is. We've talked about in the past where in the last lecture that the total effect of a price change is equal to the substitution effect of a price change plus the income effect of a price change. Well, the total effect is the derivative of demand for coffee with respect to price. And so what we're going to fill in the blank is the mathematical expressions for the income effect and the substitution effect. That's kind of the goal for today, is to write a mathematical expression that will illustrate this. But we need to fill in some background or some foundation first. Okay, so this is the goal for today. Let's jump right in. All right, so I'm going to split the screen in half, and we're going to have a conversation. Okay, so when I started this series of lectures on demand functions, what I talked about was how the demand functions were the results, the conclusion of a utility maximization process. So basically, agents choose coffee and bagels to maximize their utility subject to their budget constraint. All right, subject to their budget constraint, and this maximization process results in coffee and bagels, which is a demand function. All right, so I've kind of hit this several times. All right, demand for bagels as a function of the price of bagels, taking PC and income as parameters. Okay, but now if you remember from our discussion of individual decision making, agents might choose consumption based on utility maximization, but we could also think of what we call the dual problem. Remember the dual problem, the duality, the dual problem of expenditure minimization. So they might choose coffee and bagels to minimize their expenditures, subject to the constraint that they need to achieve a certain level of income. A certain level of utility. All right? That means they might choose coffee and bagels that will minimize their expenditures, but allow them to achieve a fixed level of utility. All right? So if they did expenditure minimization, they're also going to solve for C star and B star. Well, now in this lecture, we are going to relate these two in a more meaningful way. Because what we are going to find, or what we're going to realize in today's lecture, is that these are demand functions, so the solutions to the utility maximization problem are demand functions, and the solution to the expenditure minimization are demand functions, but they're actually two different kinds of demand functions. All right, so let me define these two. The functions that we derive from utility maximization are called Marshallian demand functions. Marshallian demand functions, or we might call them uncompensated demand functions. All right, they're uncompensated demand functions. What do I mean when I say uncompensated? Uncompensated means they the agent is not, I'm going to write it differently. Yep. The agent is not given income to compensate for price changes. All right, that's one way of putting it. Another way of putting it would be this. Income is held constant. Utility is not. Okay. Well, what are these called? If we do an expenditure minimization, we get demand functions. We label them differently. We use the letter H. So H is it's a different kind of demand function. I'll show you why it's the letter H in a second. It's a demand function. It gives you the quantity demanded as a function of the price, taking the other prices as parameters. Okay, so this HC, this is a demand function for coffee as a function of the price of coffee. Here is a demand function for bagels as a function of the price of bagels. Okay, but we call these the Hicksian demand functions. So they're demand functions. They're just a different kind of demand function. We also call them the compensated demand function. What do I mean by compensated? Let's do a different color. What do I mean by compensated? Compensated, what I mean by that is the agent is given income to compensate for price changes. All right, another way of putting it would be that utility is held constant while income can vary. Or it's not held constant. Not constant. So for uncompensated demand functions, and maybe I'll as an aside, these are the primary functions that we concern ourselves with. They're kind of the main ones. They're kind of the main demand functions that we concern ourselves with because in reality, people are not given income to compensate them for price changes. So we'll focus on these in a sense. But uncompensated demand functions are demand functions that take prices as inputs and communicate the quantity demanded as a function of the price. And it holds income as constant. Oh, actually, I made a mistake. That'll actually help me to illustrate this. Sorry for those following along. This is an important distinction. Okay? This is an important distinction. The uncompensated demand functions take income as a parameter. That means it's fixed. Income is fixed. Okay? The compensated demand function takes utility as fixed. So implicitly in these demand functions, utility is allowed to change. So utility can change. Implicitly in these demand functions, utility doesn't change, but income can change. Okay, so we have two different kinds of demand functions. We have the compensated demand function, we have the uncompensated demand function, and we have the compensated demand function. These two different functions are going to be important for us in terms of understanding the relationship between a price change and demand. All right, so here are the two different demand functions. Now I'm going to delete this and we're going to go into some more detail. All right, so we have two different demand functions. Now I could just plot those two different demand functions to give us an illustration of what it would look like. So here's coffee, price of coffee. All right, light blue here, this is going to be the demand curve for coffee. That means uncompensated. And then this purple is going to be the compensated. They will intersect at a single point. So these are two different demand functions. They exhibit the same characteristics. They're both downward sloping. That means there's an inverse relationship between price and quantity. The higher the price, the lower the quantity. All right. They're both downward sloping. They exhibit similar characteristics. However, at every point on this demand curve, at every point on the uncompensated demand curve, at every point on this curve, income is constant. Income is constant, but the utility that the agent achieves at any point on this demand curve, utility may be different. So what do I mean by that? That means, let's say I had this point A, and I had this point B. These are two different points, so point A and point B. So point A and point B, let's just use red again. All right. So point A and point B are on the uncompensated demand curve. That means at point A, so this is some possible combination, so some possible quantity demanded given some particular price. All right. So at point A and point B, the agent's income is the same. Is the same at A and B. The agent's income is the same. The utility that they derive from consuming B at point B, the utility is different, or probably different. Okay, now alternative option. Let's do it. So let's say here's point C and point D. On the compensated demand curve, point C and D, at both of these points, at both of these levels of consumption, let's see, at both of these levels of consumption, the utility that the agent achieves, utility, is the same. But income is different. So that means, so here at D, the agent is able to consume a larger quantity of coffee than they are here. Well, how in the world would they achieve the same amount of utility at point C? How would they achieve the same amount of utility at consuming CD as CC? How do they achieve the same amount of utility? Same utility. Because we would think that they would achieve higher utility at CD because they're consuming more. And if we remember from our preferences lecture, that more is always better to a rational agent. And so how could we possibly say that they have the same utility whether they consume CD or CC? How could that be? Well, because when we're using the compensated demand, when we're using the compensated demand, income changes. That means that at point D, or at point C, actually no, point C, at point C, income must be higher. Income is higher to compensate for the higher price. Okay. So this shows us the relationship between the uncompensated, and the compensated demand curves. Now, let's go a little bit deeper. Okay? I'm going to erase this. Let's go a little bit deeper. Let's kind of go back to last lecture for a second. Remember, we went through detailed descriptions of the effect of an increase in the price on demand. Let's do this. Okay. All right, so this should look pretty familiar. Oops. Okay. And then we drew, and it was kind of a funny idea, this light blue line, trying to illustrate the substitution effect. It's kind of a oh man, that's awful. Okay. It's kind of a funny idea, this light blue line, right? It's supposed to capture the substitution effect. So it might have sounded kind of peculiar as I drew it and illustrated it, but the idea behind this light blue line was that imagine if price went up from PC up to PC prime. Okay, so price goes up. So price goes up from PC to PC prime, but agent is given income to compensate for the price change. And by compensate, that means that they have enough income to achieve the same utility. All right. So basically, when we're talking about illustrating the substitution effect, we are illustrating the difference between the uncompensated demand and the compensated demand. So basically, here's my point. This whole idea of this compensated line here allows us, so here's coffee demanded. All right, so here's coffee demanded at bundle A, and then here is coffee demanded at bundle B. Let's just be consistent here. Coffee demanded at bundle C. Okay. Okay. So the effect of the price on demand can be illustrated in two ways. Remember, there are two demand functions. There is the uncompensated, and then there is the compensated, right? And so we get an idea of both of them from our illustration before. So the uncompensated means that income remains the same and utility is different. That is illustrated by what we call the total effect. The total effect. So how does an increase in price affect demand for coffee? Well, it affects demand because it moves from CA to CB. This is the total effect. This total effect is equivalent to the effect of a price change on DC, the uncompensated demand. Why do we call it uncompensated? Well, remember, when we increase the price, what's happening is that utility is different, right? Because we move from this indifference curve to this indifference curve. So when we increase the price, the indifference curve changes. All right. So when we increase the price, utility changes because now we're on a different indifference curve, so we have a lower level of utility, but income remains the same. Your income on the first budget line is the same as the income on the second budget line. Now the purchasing power of that income is different, but strictly speaking, the income itself is held constant. So that means the total effect represents the change in price on the uncompensated demand because income is constant, utility changes. All right. So the total effect, the difference between CA and CB captures the total effect, which is the effect of a price change on the uncompensated demand. Why is it uncompensated? Well, because when we move from A to B, we are changing the level of utility. They get less utility at bundle B, but income remains the same. Why does income remain the same? Well, I can illustrate that. So here I'm going to use purple for the original budget line, blue for the second budget line. All right, so the purple budget line, the original, let's say that it's income equals PCC plus PBB. And then we have the second budget line. So we're saying that the price increases. The income remains the same. Same level of income. Same price of bagels, okay. But the price of coffee goes up. So we're saying that PC is greater than PC. Okay. So income, here's the main point, here's the takeaway message. Income remains the same. So when we look at bundle A and bundle B, income remains the same, utility changes. Okay. Now, if we want to look at the compensated demand, that means we're going to compare bundle A with bundle C. Why is that? Well, so that would be that. Okay, let's show it down here. We're going to compare bundle A with bundle C. Before we called this the substitution effect, but what we're going to see here is that the substitution effect is, all right, let me do a different color. Let's do orange. Substitution effect. We call this a substitution effect. The substitution effect is the effect of a price change on the compensated demand curve. Well, why is that? Well, I think we can see it pretty clearly. When you look at the substitution effect, you're looking at holding utility constant. So utility is constant, but income changes. Income changes. Your income increases. So if we look at this budget line, we called it budget line squiggle. Budget line squiggle has an income level that is higher. Budget line squiggle has an income that is higher than before. Income squiggle is greater than the original income. It's greater than the income. They are given additional income in order to compensate them for the increase in price. So it still has the original price of bagels, and it has the new price of coffee, but it has a higher level of income. So that means utility is held constant, but income changes. So the difference between demand at point A and point C, we called it the substitution effect. This is the effect of a price change on the compensated demand curve. All right, so we're just relating these concepts to last lecture. There are two different kinds of demand functions. One, the uncompensated demand. The other is the compensated demand. For the uncompensated demand, utility can change, income is held constant. For the compensated demand, utility is constant, income can change. Now, let's make this more mathematically formal. To make this more mathematically formal, I'm sure that makes you abundantly excited. All right, so I'm gonna draw this up here, C and PC. I just kind of want to have this in the back of our minds as we talk here. So here is the uncompensated demand. Here is the compensated demand for coffee. All right, so let's just have that up there in the background. I want us to remember a duality condition. We're going to use this as a basis to relate these mathematically. Duality condition, you remember that if we solve for C star and B star using a utility maximization process, and then we plug them back into the utility function, we would get what we call the indirect utility function, or sometimes the value function, V, which is a function of the prices and income. Okay, so this would be the consequence of a utility maximization. Okay, if we did an expenditure minimization, then we would end up with the optimal expenditure function, which is a function of the price. We do expenditure minimization. We will find a C star and a B star, which we now know are the Hicksian, or the compensated demand functions. We take those, plug those back into the expenditure function, and we're going to get the optimal expenditure function, which is a function of the prices and some given level of utility. All right, so we have these two functions: the indirect utility function and the optimized expenditure function. Whoops. Okay, and this indirect utility function is a function that gives as an output some value of utility. It's optimal utility, and this gives as an output the minimized level of income, or minimized expenditures. Okay. And we showed that these two relate to each other in a given way. That means, well, this is how they relate. If I take the expenditure function, I plug it into the value function. So let's say I do that. PC. Let's do this. Okay. PC, PB. Instead of having I plug in the expenditure function. That's going to give me utility bar. And the same thing is true if I take the value function and plug it into the expenditure function. If I have the optimized expenditure function, and instead of having utility here, I plug in the value function, or the indirect utility function, I will get income. Now, this is duality condition. It means they relate to each other. Okay. So what this means is that the value function intersects with the expected utility function at one point, and that is this point. There's one point at which these demand functions intersect. There's one point at which these demand functions intersect. It's related to this duality idea. So this is the duality idea, the relationship between utility maximization and expenditure minimization, where we would say this. The compensated demand function oops, equals the uncompensated demand function but so normally we have income here, but instead of income, what we're going to do is we're going to plug in the expenditure function. So all right, PC, PP, utility. All right. So this is how we're going to relate them. We're using duality to relate the two demand curves. So basically what we're going to say is, so normally I would have my uncompensated demand function is a function of prices, and then it's a function of income. Well, we're gonna instead of having income here, we're gonna plug in the optimized expenditure function. So it's going to be income at the optimal point, the optimal level of income. And we're saying that the uncompensated demand curve is equal to the compensated demand when the income is at the optimized level. So this point here, this equality is achieved at this point. So at one point, the compensated demand function intersects with the uncompensated demand function. All right, this equation is going to form the basis. This equation is going to form the basis for how we're going to relate these two different demand curves. All right, so I'm going to use this equation to relate these two different demand curves. Okay. So what I'm going to do is I'm going to do something that you might not be happy with, and that is I want to create I want to take a total derivative. Now remember here, my ultimate goal, I'm working my way, so I started the lecture this way. I want to know the effect of a change in the price on demand, right? This is my ultimate goal. I'll keep this up here on the top. We're going to work our way towards that. But first, for us to know the total effect of demand, we need to have some way of capturing the substitution effect. We need to capture the substitution effect, and we need to capture the income effect. Well, the only way that we can capture the substitution effect is by looking at the compensated demand function. We need to be able to look at the compensated demand function because I've already shown you graphically that the compensated demand function accounts for the substitution effect. Okay, so I need to be able to relate these two. Just a moment ago, I showed you how I can relate the compensated demand curve to the uncompensated demand curve, or the compensated demand function to the uncompensated demand function. So now I need to use this relationship that I've established using duality. I need to use this relationship to allow me to derive this expression. Okay, that's what I'm doing. All right, that's the story. So what we're going to do is we're going to take a total derivative. I want to take a total derivative of the compensated demand curve with respect to the price. Take a total derivative. Why am I saying the total derivative? Why am I saying the total derivative? Well, because the compensated demand curve is equal to the uncompensated demand curve, and they're equal to each other at the point where income is equal to that optimal, that maximized expenditure function level of income. All right, so why is it a total derivative? Well, because with the optimal expenditure function plugged in, with the optimal expenditure function plugged in, the uncompensated demand curve is directly a function of the price of coffee, and it is indirectly a function of the price of coffee, which means we need to take a direct derivative and the chain rule partial derivative. All right, so that's what we're going to do. We're going to take the total derivative. We're going to take the total derivative. So that's what we're doing here. Total derivative. All right, so when you take the direct derivative, that means the derivative of dc with respect to pc. This is a good sign. This is what we ultimately want this. All right, plus, now we need to apply the chain rule, the derivative of dc with respect to e, that optimal expenditure function. All right, that's the outer function. The outer function here is the dc, multiplied by the derivative of the inner function, derivative of e with respect to pc. All right, so now, like I said before, we are trying to solve for this. We want to get this. This is what we want to find. So let's reorganize the terms here. So the total effect of a change in price is equal to the effect of a change in the price on the compensated demand curve minus this other term. Okay. Now, I'm going to kind of give this away a little bit here. I'm going to kind of give away the conclusion a little bit to whet your appetite. So this is the total effect of a price change on the uncompensated demand. This is the substitution effect, which should give us an indication that this might be, or maybe I'll ask the question, what is this? And then, of course, in the back of our minds, so if you're there and you're thinking about this, in the back of your mind, you might be thinking, is this the income effect? Well, let's see. All right. I'm going to erase all of this. I'm going to write this equation up in the corner, and then we are going to we're going to continue with our calculations. All right. So the total effect of a price change is equal to the effect of a price change on the compensated demand minus this other term. And so what I'm going to spend a couple minutes doing is trying to show you what this other term is. What this other term means. Okay. So I want to say, well, what is this other term? Well, let's remember a couple things. First, let's remember that E, this is the optimal expenditure function. We get this from solving the expenditure minimization problem and then plugging the optimal values back into the expenditure function. This is a function that gives us income. The output of this function is income. Okay, so then I could rewrite this as this. So I'm going to rewrite the derivative of the demand for coffee with respect to income. And I can rewrite this as the derivative of income with respect to price. All right, so I'm going to do that. I'm going to rewrite this equation now. We're starting to get a clearer picture of how the second term here is the income effect. So the change in demand given a change in income. Change in income given a change in price. Okay. Now we're going to simplify this further. I'm going to leave this as an E for now. I'm going to get rid of this term in just a minute. The next thing I'm going to do is get rid of this term. I'm going to simplify this term, show you what this means. All right, so let's do that. Let me try to show you what this term is. I'm going to show you what this term is. going to show you what this term is. We're going to get rid of that, and then we'll be done with this equation. What is this? All right, so remember, E is a function of PC, PB, and utility. All right. So when I say the derivative of E, what I really mean is the derivative of this optimized function. Okay. Now remember where we got this. Remember where this came from. This came from an expenditure minimization problem. We chose coffee and bagels to minimize the expenditures subject to a utility constraint. All right, that's where this came from. We solve this problem. We get C star and B star, which we now know are equal to our compensated demand functions. Compensated demand. We take these values, we plug them back into the expenditure function. So PC C star plus PB B star. All right, so then this function E of PC PB U is equal to PC C star plus PB B star. All right, so that's what this function is. This expenditure function is a function. So the expenditure function is a function at its maximum. So it's a function at its maximum. That's what this function is. It is the expenditure function at its maximum point. It is now a function of the parameters of the model rather than the variables, because the variables have been optimized and plugged back in. So this is a function at its maximum. So now if I wanted to say, what is the derivative of this function with respect to C, all I need to do to know the answer to that question, you know what, I'll rewrite this. All right, I need some more space. Let's leave it. All right, so this is a function at its maximum point. It is equal to PC C star plus PB B star. It's a function at its maximum. If I want to know what is the derivative of this function with respect to PC, all I do is I apply the envelope theorem. Which means the derivative is just the direct derivative, which means I just take the derivative of this equation. That means the derivative of E with respect to PC is just equal to the derivative of this equation. It's just equal to C star. Done. It's just equal to C star. So now I can take this, apply the envelope theorem. The envelope theorem in this particular context, this is called Shefford's lemma, if you care to be interested. Okay, and so what we can do now is I'm going to rewrite this equation here, having simplified everything. So now the total effect of a price change on uncompensated demand is equal to the effect of a price change on compensated demand minus the effect of a change in income on demand multiplied by that demand, which maybe we'll just get rid of the star for now, multiplied by the demand. This equation here, which I'm going to erase everything else and write this up at the top, or write it real big. This demand, this function here, this equation here, let's see, what color should we use? I like my different colors. Okay, this function here is called Slutsky's equation. It is the effect of a price change on uncompensated demand is equal to the effect of a price change on compensated demand minus, see, this other term here. And what we'll see here is that Slutsky's equation gives us a mathematical expression. So this is Slutsky's equation. And so what we find here is, actually I'm going to explain it, is a mathematical expression for the effect of a price change on demand. So Slutsky's equation gives us an expression, a mathematical expression for the effect of a price change on demand. All right, I didn't give myself enough room here. So let's explain it. So this, in terms of our discussion from last lecture, this is the total effect of a change in price. This is the substitution effect. And then this term here is the income effect. Okay, so when price goes up, the Hicksian demand curve is always negative. The Hicksian demand curve, the compensated demand curve, is always negative. That is, the derivative, this derivative is always unambiguously negative. When the price goes up, the compensated demand always goes down. That's always negative. This term here, this is our income effect. This is where it gets interesting. Now you can see this elasticity embedded in the math. Remember, elasticity of demand, income elasticity of demand is equal to the derivative of demand with respect to income times income divided by demand. Okay. And so what we can see here, we can see the effect of income on demand in the equation. So what we have here is this term here shows us the effect of income on demand for coffee. So if this term is positive, that means an increase in income. If an increase in income leads to an increase in demand, that means it's a normal good. If it's a normal good, then this whole term here will be positive. This term here will be positive, and because we subtract it, the net income effect will be negative for a normal good. Which means that the total effect will be negative, because it's a negative minus a positive, which is a negative. So the substitution effect is negative, income effect is negative. However, if demand goes down as income goes up, this would be an inferior good. That would mean that this whole term here instead is negative. And so if you subtract a negative, that would imply that the income effect is positive. So now the total effect will still be negative so long as the substitution effect, the absolute value of the substitution effect is larger than the absolute value of the this expression from the income effect. As long as this is greater than this, then the total effect will is negative. As long as this is true, the total effect is negative, even for an inferior good. Okay. However, if the price effect, I'm sorry, if the income effect is larger, so if this is true, then the total effect can be positive, which implies a Giffen good. Okay, so with all that said, let me clarify one last thing. I'm going to try to make this really clear on Giffen goods, and then we're going to be done. And we're going to be done for this lecture. When we meet in class, we're going to talk about Giffen goods, so I want to make sure we understand it mathematically. So here's the Slutsky equation. Total effect equals substitution effect we've got our income effect here. Whoops. Okay. So a Giffen good has the following characteristics. A Giffen good is that the good has to be an inferior good. The good is an inferior good if this is negative, because if this term here is negative, when you subtract a negative, that's becomes positive, right? Okay. So if you have an inferior good, and if the income part of the equation is greater than the substitution effect, then you will have a Giffen good. So basically, if these two things are true, you'll have a Giffen good. That means that an increase in price will result in an increase in demand. This is the Slutsky equation. We explained it, we derived it, we went into extensive detail on it. Okay, great. I hope you have a great rest of your day. Thank you for listening.